Hello dear students, welcome to ECE Academy Benefactor. In this class we will be seeing design of FIR filter using Hanningwindow. Let us start the problem. Design an ideal high pass filter with a frequency response HD of e to the j omega is equal to 1 for pi by 4 less than equal to mod omega less than equal to pi. In this range, that is in between minus pi by 4 and pi, and minus pi to minus pi by 4, its value is 1 and is 0 for mod omega less than equal to pi by 4. So, the desired frequency response of ideal high pass filter is given. Find the value of h of n for capital N is equal to 11. Find h of z using Hanningwindow. We have done this problem in the previous class using Fourier series method, which you can find it in the playlist in the I window. Let us start the solution. Design of FIR filter. The steps required are HD of e to j omega, that is a desired frequency response. From this we find HD of n, that is a desired impulse response. This is of infinite nature, and then next step is to find Hanningwindow coefficients, and then finding truncated impulse response. This can also be called as filter coefficients. This is HD of n filter coefficients. This is of infinite nature, and as we are designing FIR we need truncated h of n. So, we are multiplying this to HD of n and WHN of n Hanningwindow to get h of n. Based on this h of n, we are finding transfer function of the filter h of z, and from h of z we find h dash of z, which is physically realizable transfer function. This h of z will contain positive powers of z, so it cannot be physically realizable. So, we have to multiply this h of z with z to the power of minus of n minus 1 by 2 to get h dash of z. The first step is HD of e to j omega, the desired frequency response is written here, which is equal to 1 for pi by 4 less than equal to mod omega less than equal to pi, and is 0 for mod omega less than equal to pi by 4, which is drawn here. So, this is known, this graph is known as ideal response of this is known as a frequency response of ideal high pass filter. Its value is 1 between pi by 4 and pi, and minus pi to minus pi by 4 mod value. So, its value is equal to 1 in this range. For mod omega less than pi by 4, mod omega less than pi by 4, its value is 0. So, based on this desired frequency response, we can draw the frequency response graph of an ideal high pass filter, which is already given in the question. Second step is to find HD of n, that is a desired impulse response or the Fourier coefficients, which is given by the formula HD of n is equal to 1 by 2 pi integral of minus pi to pi HD of e to the j omega and d omega. In this we have to split this integral. The integral will range from one part will be from minus pi to minus pi by 4, plus another integral will be pi by 4 to pi, because in this range only its value is equal to 1, HD of e to j omega value is equal to 1. So, this step is written into this way: minus pi integral minus pi to minus pi by 4 HD of e to j omega value is 1, e to the power j omega and d omega, plus pi by 4 integral pi by 4 to pi HD of e to j omega value is 1, dot e to the power j omega n d omega. So, we have to integrate e to j omega n d omega. So, what is the answer? As we are integrating with respect to omega, we will get e to the power j omega n by j n. Okay, e to the power j omega n by j n. So, on integration we are getting e to the power j omega n by j n, limits ranging from minus pi to minus pi by 4 plus e to the power j omega n by j n ranging from pi by 4 to pi, and then substituting the limits of omega and taking this n outside and bringing 2 inside. Okay. So, it is written as pi n, 2j is written inside. So, substitute omega value here as minus pi by 4. So, we can write it as e to the power minus j pi by 4 n minus e to the power of minus j pi n, substituting the higher limit and then the lower limit, plus substitute omega as pi by 4, e to the power j pi n minus e to the power j pi by 4 of n by 2j. Okay. So, here we can rearrange the terms as like this: e to the power j pi n minus e to the power minus j pi n. These two terms we brought it together and written by 2j. E to the power of j pi by 4 of n, it is minus, so taken minus out, e to the power j pi by 4 n minus e to the power of minus j pi by 4 of n by 2j. So, collecting the terms in this way, it appears like this in this form: e to the power j theta minus e to the power minus j theta by 2j is equal to sin theta. Okay. So, e to the power j theta minus e to the minus j theta by 2j. So, what is theta here? Pi n. What is theta here? Pi by 4 of n. So, this is sin theta, this is equal to sin theta, theta is equal to pi n. So, sin pi n minus sin of pi by 4 of n. So, we found HD of n. Okay. So, after getting, we have to find, as capital N value is 11, we have to find HD of 0, HD of 1, HD of 2, HD of 3, HD of 4, HD of 5. HD of n is coming to be as sin pi n minus sin pi by 4 n by n pi. To find HD of 0, by substituting n is equal to 0 directly, this becomes indeterminate. So, what we do? It is infinite. So, we make limit n tending to 0, limit n tending to 0 for this equation, instead of directly putting as n is equal to 0. So, what happens? Limit n tending to 0 sin n pi minus sin pi by 4 by pi by 4 n by n pi. This solution also we can see in the previous video, which you can see in the DSP FIR filter playlist or in the above I button. Okay. So, on simplifying this one, we will get HD of 0 as 0.75. Now, from 1 to 5 we can directly substitute n is equal to 1. So, now substitute HD of 1 is equal to HD of minus 1. Why we are writing like this? Because it is symmetrical in nature. Symmetrical impulse response, H of n is equal to H of minus n. So, it is written as sin n pi minus sin pi by 4 by pi. Substituting n is equal to 1. So, we will get sin pi minus sin pi by 4 by pi. So, we are getting it as minus 0.225. Next, HD of minus 2, which is equal to HD of 2, which is equal to, now substitute n value as 2. Sin 2 pi minus sin pi by 2, 2 pi, which is coming to be as minus 0.159. Next, find hd of minus 3 is equal to hd of 3. Substitute n value as 3. Sin 3 pi minus sin 3 pi by 4 by 3 pi. On simplifying, we are getting it as minus 0.075. hd of minus 4 is equal to hd of 4, which is equal to h sin of 4 pi minus sin pi by 4 pi, which is coming to be 0. Next, we will find hd of minus 5, which is equal to hd of 5, which is equal to sin 5 pi minus sin pi by 5 pi by 4 by 5 pi. It is coming to be as 0.045. Next step is, after finding the hd of n from hd of 0 to hd of 5, next we have to simplify the Hanningwindow. Hanningwindow definition is given by, its Hanningwindow's notation is WHN of n, which is equal to 0.5 plus 0.5 cos 2 pi n by capital N minus 1, and this small n is varying between minus of n minus 1 by 2 to capital N minus 1 by 2. Is equal to 0.5 plus 0.5 cos 2 pi n by n minus 1 in this range and is 0 otherwise. So, on substituting, capital N value is given as in the question as 11. So, n minus 1 means 10 by 2, that is 5. So, small n is varying from minus 5 to 5. So, the definition of Hanningwindow becomes WHN of n is equal to 0.5 plus 0.5 cos pi n by 5, ranging between minus 5 to 5 and is 0 otherwise. So, after simplifying this small n value, we have to find the Hanningwindow values, that is WHN of 0. What you have to do for finding a WHN of 0? Substitute n value as 0 in this one. So, what it becomes? Cos 0. So, here it is written as 0.5 plus 0.5 cos 0. Cos 0 is 1. So, it is written as 0.5 plus 0.5, which is coming to be as 1. Now, find WHN of 1 is equal to WHN of minus 1, because we know the weighing window functions are symmetrical in nature. So, we can write WHN of n is equal to WHN of minus 1 because of symmetrical impulse response, symmetrical way in nature. So, now substitute n is equal to 1 in this above equation. So, it becomes 0.5 plus 0.5 cos pi by 5, which is coming to be as 0.9045. Next, find WHN of 2, which is equal to WHN of minus 2, which is equal to 0.5 plus 0.5 cos 2 pi by 5, coming to be as 0.655. After finding WHN of 0, WHN of 1, WHN of 2, now substitute n is equal to 3. WHN of 3 is equal to WHN of minus 3, which is coming to be as 0.5 plus 0.5 cos 3 pi by 5. On simplifying, it is coming to be as 0.345. N is equal to 4. WHN of 4 is equal to WHN of minus 4, which is coming to be as 0.5 plus 0.5 cos of n value is 4, cos 4 pi by 5. On simplifying, it is coming to be as 0.0945. Next, n is equal to 5, we will get WHN of 5 is equal to WHN of minus 5, which is equal to 0.5 plus 0.5 cos pi, which is coming to be as 0, because cos pi is minus 1. So, in this way we computed WHN of n for n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, and we know because of symmetrical nature Whn of n is equal to Whn of minus n. Okay. Next step is to find filter coefficients using Hanningwindow. So, what we have done till now, we have computed Hd of n and Whn of n. This is infinite nature because here n is varying between minus infinity to infinity. So, this is an infinite sequence and Whn of n is a finite weighing sequence. Now, multiplying these two equations, we will get h of n, which will be finite impulse response. So, based on this, we can compute what is h of z. So, h of n is known as filter coefficient or also known as finite impulse response. So, here I have given the heading as filter coefficients using Hanningwindow. H of n is equal to Hd of n dot Whn of n for minus phi less than equal to small n less than equal to 5 and is 0 otherwise. So, we got the values of h of 0, Whn of 0. So, in the previous part, so we have written h of 0 is equal to Hd of 0 dot Whn of 0. Hd of 0 value we got it as 0.75, Whn of 0 value is 1. On multiplying we get it as 0.75. So, the h of minus 1 is equal to h of 1, which is equal to Hd of 1 dot Whn of 1, which is coming to be as minus 0.204. Next, we find h of minus 2. H of minus 2 is equal to h of 2 because of symmetrical nature, which is equal to Hd of 0 dot Whn of 2, which is coming to be as Hd of 0 value is minus 0.159 dot 0.655 and it is obtained as minus 0.104. H of minus 3 is equal to h of 3, which is equal to Hd of 3 dot Whn of 3. On simplifying, we are getting it as minus 0.026. H of minus 4 is equal to h of 4, equal to Hd of 4 dot Whn of 4, which is coming to be as 0. H of minus 5 is equal to h of 5, which is equal to Hd of 5 dot Whn of 5, which is coming to be as 0. So, we got h of 4 and h of 5 as 0. So, what we are doing here? We are multiplying infinite filter coefficients with the finite weighing sequence to get finite filter coefficients h of n. After obtaining this h of 0 to h of 5, we will find the transfer function of the filter. The transfer function of the filter is given by the equation h of z. H of z is equal to h of 0 plus summation n is equal to 1 to capital N minus 1 by 2. H of n dot z to the power of n plus z to the power of minus n. H of 0 value we got it as 0.75. H of 0 value we got it as 0.75. Okay, which I have substituted it here. Plus summation n is equal to 1 to 5 because capital N value is how much? 11. 11 minus 1 is 10 by 2, 5. Okay. H of n, z to the power of n plus z to the power of minus n. Now open this series, putting n value from 1 to 5. 0.75 plus h of 1, n value is 1, h of 1 z to the power 1 plus z to the power minus 1 plus, now n value 2, h of 2 z to the power 2 plus z to the power minus 2. Now n is equal to 3, h of 3 z to the power 3 plus z to the power of minus 3. N is equal to 4 plus h of 4 z to the power of 4 plus z to the power minus 4. plus h of phi is z to the power 5 plus z to the power minus 5. So, on substituting, we will get h of z as 0.75 minus 0.204 z to the power 1 plus z to the power minus 1 minus 0.104 z to the power 2 plus z to the power minus 2 minus 0.026 z to the power 3 plus z to the power of minus 3. Z to the power h of 4 and h of 5 are 0. So, we have not written those terms. Okay. So, what we have done, we got h of n and then found the transfer function. So, as you see in this part, h of z is containing positive powers of z. So, it is not physically realizable. Next step is to find h dash of z. The transfer function of physically realizable filter is h dash of z. We got h of z, now we have to find h dash of z, which is equal to z to the power of minus of n minus 1 by 2 dot h of z. N value is how much? 11. 11 minus 1, 10 by 2, which is coming to be as 5. So, h dash of z is equal to z to the power of minus 5 dot h of z. H of z equation we got it. Multiply that with z to the power minus 5. On simplifying this, we will get h dash of z, which is coming to be as minus 0.026 z to the power minus 2 minus 0.104 z to the power minus 3 minus 0.204 z to the power minus 4 plus 0.75 z to the power minus 5 minus 0.204 z to the power minus 6 minus 0.104 z to the power minus 7 minus 0.026 z to the power minus 8. So, it is containing all negative powers of z, so it is physically realizable. Okay, so by this we complete the solution for the design of FIR high pass filter using Hanningwindow. So, let me quickly summarize what we have done in this solution. HD of e to the j omega is given, which is known as desired frequency response. First, we have computed HD of n, which is infinite in nature, computed with the help of the formula 1 by 2 pi integral minus pi to pi HD of e to j omega dot e to j omega n d omega. And then we have written the definition of Hanningwindow WHN of n and found, and then after finding WHN of n, we have computed H of n, that is finite filter coefficients, which is equal to HD of n dot WHN of n. We will get H of n. And then we have obtained H of z, the transfer function of the filter. That is not physically realizable, then we are computing H dash of z. I hope you have understood the class. If you have any queries, you can post in the comment section. Thank you. Good luck, students.